Hello and welcome to the second class of Logistic Regression. In the previous class, we already had the motivation for studying Logistic Regression. It helps us understand the association between categorical variables with the help of odds ratio. So, for example, we have a response variable which only has two values 0 and 1, and also a predictor variable which also has values 0 and 1. So, of course, we are going to have values like this, and hence it is not going to be possible for us to pass a regression line between these cluster of points, or in other words, we won't be able to run a very simple linear regression model between y and x, because to run a regression model we require many different values of the x and y variables. So, since we are not able to regress y on x directly, we can maybe try to regress probability of y on x. So, the equation becomes probability of y equal to the intercept plus the slope into values of x. So, this means probability of y equal to 1 and probability of y equal to 0. Now, probabilities are always between 0 and 1, but a regression model like this can never ensure that the outcome is going to be between 0 and 1. Hence, this model also is not feasible. Model the odds ratios or the log of odds ratios instead of the probability directly. We know if probability is p of y, odds would be p of y by 1 minus p of y. The suggestion is to regress the log of odds on x, or in other words, the regression model would look like equal to some intercept plus a slope into x, and this can have any value between minus infinity to infinity. Hence, we do not need to worry about the right hand side resulting in an outcome between a specific interval 0 or 1. A model like this is called the logistic regression model. Why? Because this function is called the logit function or the log odds function. Now, instead of saying that we are regressing the log of odds on x, we can also say we are regressing the odds on x like this. It's just that it's no more a linear regression, rather we have a non-linear function. And oftentimes in qualitative variables, be it categorical or count, we use some other form of regression, or in other words, we use some function to convert our required response as a linear model on the predictor set. So, here we are assuming that our odds can be modeled on x, may not be linearly, but as the exponential function, hence, or in other words the antilog, hence we can use the log of odds and make it linear. This function, which helps us model the odds on x as a linear function, is called the link function. Depending on the link function, the kind of regression also changes. As I told you, this is the logit function which helps us regress y on x. Whenever we are using the logit function as the link function, it is called logistic regression. And there are many other possible link functions such as the log link function, the complementary log link, etc. We will not be discussing those in this course, since in these lectures our focus is going to be only on logistic regression, which is a type of a classification model, since it helps us predict the response feature into one of the few classes or categories. Now, if you recall, in a regression model, beta 1 used to correspond to the amount of change in y for 1 unit change in x. But now, beta 1 tells us about the amount of change in the log of odds of y for 1 unit change in x. So, here a positive beta 1 value actually increases the odds by e to the power beta 1. So, here a positive beta 1 value indicates that 1 unit change in x increases the log of odds by e to the power beta 1. We will explore this more with the help of an example. But before we move on to the example, there is one thing that I would like to point out, that is, the estimation procedure in linear regression was least square. However, we also explored maximum likelihood equation, and we observed that the maximum likelihood estimators for the regression coefficient and the least square estimators are the same. In logistic regression, we are not in a position to calculate the least square estimates of the regression coefficient. So, we employ maximum likelihood estimation to calculate beta naught hat and beta 1 hat. And the likelihood equation looks like this: product of all the xi's and product of 1 minus probability of xi. Now, let us start with an example to understand how to interpret the coefficients of a logistic regression. To understand logistic regression in R with the help of an example, I am going to install the library ISLR. Why? Because it contains the data set default, which is a credit card default data set with a few variables such as income, balance and student status. I want to use this data set as a demonstration on how to implement logistic regression. So, for that I will first install the library ISLR. Make sure install dependencies are checked and I click on install. This installs the library ISLR onto this system. Now, if I want to use any function or data set from this library, I will need to first attach this library onto this R session. Then I will attach the default data set again onto this session, and let us take a look at how the data looks like. As I said, there is a credit card default data set. So, there is a default status, there is a student status, balance and income. If we want to know more about this data set, we can open its help file, which tells us that it has 10,000 observations on these 4 features. We can of course look at the summary of the different features. As you can see, default is a categorical variable, so the summary only gives us the counts for the different categories. On the other hand, balance is a numeric feature, hence we get the 5-point summary including the median for summary when we ask R for summary. Now, if we want to model default on balance, we can first explore the association between them visually with the help of a box plot. As you can see that balance tends to be much higher for defaulters as opposed to non-defaulters, and this of course gives us a little bit of clue if there is any association between balance and default. Here from this example we can see that balance and default status are not independent of each other, but there's a higher probability of defaulting if the credit card balance is high. So, since there is an evident amount of dependence between these two features, we can try to model default status on balance, or in other words, since there is a dependence, hence we can use balance to predict the default status. So, let us try to do that. So, first we need to fit a logistic regression model. Logistic regression model is no more simple or multiple linear regression, it comes under generalized linear model. Hence, instead of the LM function, we are going to use the function GLM. Just like regression, here also we will write Y on X and then the name of the data set. Our Y is actually default, which is a categorical variable, and we want R to know that this is a categorical feature. So, we will mention as dot factor before the response variable, so that R treats it as a categorical feature. Then we have balance, which is a numerical feature. We have the name of the data set. Now, additionally over here, as you can see, I have written family equal to binomial, link equal to logit. As I was telling you, for GLM, we have different link functions based on the problem. We can have count regression, we can have logistic regression, probit regression. There are many different kinds of regression, and each of them require a different link function. Logistic regression uses the logit link function, which is the log of odds. Hence, we need to mention the link equal to logit and that the family is binomial. Once we do that, then only we can run GLM, and we are now storing it under the model fit2. I will run this model and also look at the summary output. Now, if you look at the summary output, the intercept is minus 10.65 and the coefficient for balance is 0.005. We also have the standard error, the Z value and the P value. As you can see, P value for balance is very small, almost equal to 0. This indicates that there is very strong evidence of the relationship between balance and the default status. Hence, we can conclude that the default status seems to be very strongly dependent on the balance. Now, let us look at the coefficient value. It is 0.005. What does this coefficient mean? Unlike linear regression, it does not mean that one unit change in x ensures 0.0055 units change in y. Rather, it indicates that 1 unit change in x, which is balance, increases the log of odds increases by 0.005 units. The intercept usually do not have any practical purpose. It is just used to adjust for the average fitted probabilities to the values of ones in the data. Now, let's see how we can use this model for prediction. So, let us try to predict the response if balance is equal to 1000 versus if balance is equal to 2000. So, first I am going to create a new data where balance is 1000. Then I am going to do the prediction using predict.glm for using the model fit2 for the new data which only has one data point, balance equal to 1000. I want the prediction only for the target variable or the response variable. Now, let us look at the prediction for balance equal to 2000. Now, as you can see, for balance equal to 1000, the default probability is less than 1%. But for balance of 2000, the default probability is 58%. So, obviously, there is a sharp jump between 1000 balance to $2000 balance. So, how is this prediction or predicted value calculated? So, as we have seen in a logistic regression model, we model the log of odds on x. Using the maximum likelihood equation, we calculate the two values beta 1 hat and beta naught hat. From here, we can see that probability of y is equal to e to the power beta naught hat plus beta 1 hat x plus divided by 1 plus e to the power beta naught hat plus beta 1 hat x. So, here I can use x equal to 1000 or x equal to 2000, beta naught hat equal to minus 10.5 something and beta 1 hat equal to 0.005 and calculate the values for probability of y, or in other words, the default probability for balance equal to 2000 and default probability for balance equal to 1000. Now, this particular data set has a few more features, and we would of course want to explore those features as well and see if we can include multiple features in the same logistic regression model. So, till now we have modeled a categorical feature on a numeric feature. What if we are to model a categorical feature on another categorical feature? We can do it in the same way that we have done before. We can use the GLM function, mention the two features, the name of the data set, and then finally we will need to write family equal to binomial, link equal to logit. So, we run this and now we look at the output. So, as you can see, p value for student is very less, indicating that student status and default status are strongly associated with each other. Such a strong p-value helps us reject the null hypothesis of no association and supports the alternative hypothesis of strong association between student status and default status. And since the regression coefficient is positive, this indicates that higher student status, which is student status 1, tends to increase the default status, which is default equal to yes. In simpler words, this indicates that students have a higher probability of default. So, let us try to calculate the estimated probability for students and non-students. So, this is the default rate for students and this is the default rate for non-students. For calculating this, we have used the same equation . Just that we have calculated the default rate for students by inserting x equal to 1, the corresponding beta naught and beta 1 value from fit 3, and for calculating the default rate for non-students, we have changed the x value to 0. And that is how we calculated the default rate for students versus non-students. Now, since we are seeing that all these different features seem to be significantly associated with default, hence it makes sense to include all of them in one logistic regression model. So, we do that. So, now we try to model default on the student status, balance and also income. So, again we have to mention family equal to binomial. Notice that I haven't mentioned link equal to logit anymore. That is because for and data equal to default. Here we see that income is not significantly associated with the default rate, but the credit card balance is, and the coefficient, the regression coefficient is positive, indicating that there is a higher default rate for more accumulated credit card balances. However, now if we look at student status, we see that the regression coefficient is no more positive, rather it is negative, indicating that students have a lower default rate. But is this true? When we did a simple logistic regression of default rate on student status, we had the opposite results. But how come we have such contrasting results between the simple and the multiple logistic regression? It is because one of these features have actually worked as the confounder. To be able to understand this a little better, let us try to interpret the estimated coefficient values. So, the regression coefficient for student status is now minus 0.06. So, the new regression coefficient for student status is now minus 0.6. How do we interpret this? This indicates that for a fixed value of the other predictors, or in this context, income and balance. So, for a fixed income and credit card balance, students have a lower default rate. Now, when we did not adjust for these two features, overall students had a higher default rate. But in general, student income is obviously much less. Hence, we have two predictor features here, student and income, which are probably very highly correlated. And hence, we are observing this confounding effect in this data. students will tend to have lower income, and we might explore that students will tend to have higher credit card balances. And hence, what we had observed before and also in this multiple linear regression, higher balances are leading to higher default rate. Overall, maybe having a higher default rate, but for a fixed value of the income and credit card balance, it will appear as if students have a lower default rate. We can explore this with the help of some figures, and based on the inferences, it becomes very crucial for the credit card companies as to whom they will be issuing a credit card. In general, yes, students will be at a higher default rate, but for a fixed value of income and balance, students might seem to have a lower default rate. As I said, we will explore this more with the help of some figures.